Hello, everybody. I'm back. We're back. It feels good to be back here on a Sunday afternoon. And we're getting ready to do some more essentials of compilation. Um, Pretty exciting stuff to be picking up this week. Um, just as a note of what was going on, for the past 3 weeks, I contracted SARS-CoV-2, COVID-19, on Easter, and then was sick 3 days later. Out of an abundance of caution, as well as trying to make sure that I was well enough to survive a stream, I decided to postpone them. So unfortunately, it means we're way behind where I would like to be in this project, but it is really good to be back. So I'm hoping today that we can get into chapter 4. So chapter 4 is Booleans and Conditionals, and it's a pretty essential thing in programming languages that you can test various conditions and then execute different code based on what the condition evaluated to be. So that's pretty exciting. I think we probably have a little bit of cleanup to do from last time. I glanced at it a little bit earlier, and it looks like the tests aren't completely passing. So we'll probably fix that first, and then we'll start looking at Booleans and conditionals. There's probably also some other things that, just based on my understanding what I've read of that chapter already, that we glossed over from the earlier chapters. There were a few sentences in specific places that says you should go do this, and we didn't because it wasn't necessary for that stage of compilation. But it will be necessary in this chapter. The one I'm specifically thinking about is identifying the types of each variable. So we'll have only one type in the current languages that we've been working with. But we will have Boolean types now, so things that can be true or false. So let's get to it, and we'll get started writing some more Gleam to implement essentials of compilation. All right, so I want to make sure that our tests are passing. I think they aren't. Yeah, so we need to look at this test. This is allocate registers test. And I think that we had probably an expectation that didn't match up exactly. Okay, so it looks like we expected RDX, and we're getting some variables moved around. Some register allocations. So there's either something that changed in Gleam's standard library, or maybe we have a little non-determinism in our algorithm. So we should look at that. It's interesting that it's we were expecting, so that's the left-hand side. Right, so we were expecting, is it this one? Yeah. Okay, we were expecting RDX. I want to look at these are all caller saved, which is fine. I think we had in our allocate registers pass a function that was okay. So it's interesting we're getting RSI here and not RDX. Well, here's RDX. So they just got assigned to different variables. Again, I wonder if there's some non-determinism somewhere in our algorithm. So it's like, and I mean, I guess there is some, because if two registers, or I'm sorry, if two variables have the same saturation, remember we were computing the saturation, so like what are the potential conflicts of this variable and already allocated registers. There's a potential there that it's in this pick vertex, right? There is this has no specific order coming out of graph.nodes, because if we go to that, remember this is just a dictionary fold and there's no intrinsic order to dictionaries. So I think we need to add some determinism here. And I think it's going to be, we're going to sort before we do the max. So it's going to be an int and x86 location. So this should return an order. So we're going to do case and if they're equal, then we'll compare them via the node ID. That's going to be interesting. We'll have to put an ordering on node IDs, so the x86 location. Okay, so if they're anything else, then we return that. Okay, so if we have, let me format that real quick. Okay, if they are equal in size, then we need to decide how to order x86 location. Which is this. Gleam doesn't have a notion of protocols, so I can't just implement a protocol for this. Hi, Bianca. My cat has not been used to me being in here, so she's coming for more attention. Okay, so I want to say, let's make a public function here is order location, and that's going to take A as a location and B as a location, and it's going to return an order dot order. order. Okay. And then, so what I would like to do is, so we're going to match A and B. I'm sorry, not match, case. Thinking in Rust. Okay, so if, let's make all registers less than variables. And we're going to add the missing patterns here. Okay, so variables, we can import string. And we can say string.order, right? String compare. Yeah, string compare. Let's rename this to compare location. Oh, what happened there? Here, we're not using it yet, so we'll just rename it right like that. Okay, so we'll say string compare, and this is v1 and v2. Okay, because there's strings inside there. So then if it's location var in the first argument, then we return greater than, and I want to put those up together. And then finally, if there are two registers, let's call them R1 and R2, then we need to do something else. So we had over in allocate registers this conversion, and honestly I think we just take this and what do we call it over there? Assignment to arg. Okay, we'll call it register to rank, and this is going to be a register. This is going to return an int. And then what we'll do there is let's do case R, and we're going to move this down, and let's see if we can get these lined up so I can do a bunch of multi-line edits at the same time. Okay, so now we can go we're going to get rid of this, and then we're going to delete that as well. And then we'll flip the arrows when we're done. Okay, we're closer. So let's do another multi-line. And this is like not important in the sense that, oh, what happened there? Okay, I need to put a space at the end of this line. There we go. Hey, don't step on my keyboard while I'm trying to type, please. Okay, so this is not that like this has any meaning. It's just that we need to put an order on these registers that is kind of arbitrary to satisfy like making sure that all of our that there's like a total order over that that node. Okay, so we've got a problem here. Well, we are in this module, so let's just get rid of those. Okay. All right, so we're going to do int compare register to rank R1, register to rank R2. Okay, again, this is arbitrary. This is what we used for the allocation algorithm. Notably that things that are negative, we don't want to allocate. Those are callee save registers, if I recall correctly. So we don't want to, and the thing is, you don't want to allocate a variable to RSP or RVP anyway, because those are keeping track of your stack. And RAX is used for the return value, so you don't want to allocate to that. I don't know about R11 and R15, why they are that way, but maybe we'll learn later. Okay, so now, okay, so it's saying you can remove the wrapper. That's cool. Which means we can, oops. That's just saying you don't need to create a tuple. So like in an Elixir or Erlang, you would need to create a tuple to compare the two. Okay, it just removes that, so we have a nicer syntax sugar there. Okay, so now that we've got, excuse me, now that we've got this, what I'm hoping is that, okay, so we're going to do, this is x86 dot compare location, A.1 and B.1. So, and we can get rid of the brackets there. So if we've got, if they're equal, it's like compare the size first, and then if they're equal, compare the location, and that should give us a consistent ordering of the vertices coming out of the graph. Okay, so I don't know if that's going to fix our test. It might not, but at least let's run it. Ah, I fixed it. So like my guess was right that the problem was the dictionary doesn't provide that stores these nodes doesn't provide a consistent order. So let's go ahead and make that that fix. By the way, I did update Gleam, so if you look at that, we've updated not the compiler, but the standard library and Glee unit just a little while before the stream started. So let's fix that. Fix node ordering to be consistent when allocating vertices, allocating registers. Yeah. Okay. All right, we'll push that. And now that our tests are passing again, I think that we can start to look at Chapter 4. So, Chapter 4. Okay, so the LVAR language, which is the top-level language, the most abstract that we have right now, has only a single kind of value, integers. In this chapter, we're adding a second kind of value, Booleans, to create the elif language. Of course, we're creating a new language. In Racket, the Boolean values true and false are written #t and #f. The elif language includes several operations that involve Booleans and or not, equal, less than, etc., and the if conditional expression. With the addition of if, programs can have non-trivial control flow, which impacts explicate control and liveness analysis. So this is going to be a challenge in that, like, we did a lot of hard work in explicate control and liveness analysis, and we're going to have to revisit that. So I don't know how far we're going to get in this chapter today, but just bear in mind that we're going to have to work on those phases again. Okay, so also because we now have two kinds of values, we need to handle programs that apply an operation to the wrong kind of value, such as not one. So we need to be able to do rudimentary type checking on values and variables. So there are two language design options for such situations. One option is to signal an error, and the other is to provide wider interpretation of the operation. The Racket language uses a mixture of these two options, depending on the operation and the kind of value. For example, the result of not one is false because Racket treats non-zero integers as if they were true. This is pretty typical in languages like C and Python and so forth. So on the other hand, car, which is taking the head of a list, one results in a runtime error in Racket because car expects a pair. So it's expecting head and tail. Car would give you the head of the pair. One is not a list or not a pair. Typed Racket makes similar design choices as Racket, except that much of the error detection happens at compile time instead of runtime. Typed Racket accepts not one. But in the case of car one, Typed Racket reports a compile time error because Racket expects the type of the argument to be the form of list of t or pair of t1, t2. Okay. So the elif language performs type checking during compilation just as Typed Racket does. In Chapter 9, we studied the alternative choice, that is a dynamically typed language like Racket. The elif language is a subset of Typed Racket. For some operations, we are more restricted, for example, rejecting not one. And I think that's a completely reasonable thing. If your thing is you want to negate one, then compare one to some other integer. And then you get a Boolean. So we keep the type checker for elif fairly simple because the focus of this book is on compilation and not type systems, at which there are several books. Of course, Pierce 2002, which is the types of programming languages, Harper 2016, and there's another Benjamin Pierce book. Okay, so we begin by defining the syntax and interpreter for the elif language. Then we introduce the idea of type checking, aka semantic analysis, and define a type checker for elif. To compile elif, we need to enlarge the intermediate language cvar into cif, and x86 int into x86 if. So we're going to be creating new languages, new intermediate languages. The remaining sections of the chapter discuss how Booleans and conditional control flow require changes to the existing compiler passes and the addition of new ones. We introduce a shrink pass to translate some operators into others, thereby reducing the number of operators that need to be handled in later passes. So again, this whole book is about incremental enhancement and incremental shrinking of the problem space. So as the closer you get to the assembly language, the closer or the fewer things you're going to have to deal with. And that's actually really smart because then those phases which directly operate on the registers and the stack and so forth are much simpler to understand, and which is why I've been wanting to do this approach as a project for a while. So let's look at, here's the concrete syntax of elif. So what we're going to do is we're going to make a new file like we always do, elif.gleam. I suppose eventually we will make cif and x86 if and so forth. And I feel really good that we made this base module which has the things that don't change between these different languages. So that's going to be helpful for us long term. Okay, so we basically got lint. Or I'm sorry, not lint, lvar. Lvar is a little bit more complicated. Let's look at this. So this is the concrete syntax. I want to see what they say the abstract syntax. Here we go. Okay. So elif And I'm going to shrink this so we can keep them both visible. So they're saying that a type is either integer or Boolean. And they're adding, okay, the arrangement of this is a little bit confusing because expression in the above, I guess they're just showing this is lint, this is lvar, what adds on top, and this is elif, what it adds on top. So in any case where there's an existing non-terminal, they're just adding clauses to that non-terminal. So if we go from lvar and we can get the project view out of the way. If we take this and let's just copy all this stuff in here if we need it. Excuse me. Okay, so we've got read, negate, plus, minus. We have expressions are integers, primitive operations, variables, and let expressions. So we're going to need to have something to represent this. So let's go ahead and make, we'll call it value type because we can't use type. I don't think. It's fine with that. Okay, well, it's caps, so it's all good. Okay, so we're going to have integer and Boolean. And these are just, this is just a type enum, right? Those are the two kinds of types of values that we have. Okay, so okay, so for expression, in addition to int, we have bool, and the value is bool. And this is going to be a little bit confusing because this bool and this bool are not the same. This is Gleam bool, this is elif bool. So that's an additional expression, and then in the that's a simple expression. In this one we have if, and this is going to be the condition, is going to be an expression. The then branch is going to be expression, and the else branch is going to be an expression. Now that's a reserved word, so we could use like else without an E. I don't like that. We could do something like if true, if false. There's those dang emojis. Hit the wrong key. So we could do like that. That's actually not too bad. If you've ever done the like building up a language with just the lambda calculus, you will be familiar with this if true or and if false. That's a fairly typical thing. Okay, so now we have the expressions added. So what I'm not seeing is where. Okay, so we're adding primitive operations. Okay. So the way this is worded is kind of weird. And I don't know whether we should have a separate AST type for comparison. Let's go ahead and do it though. Let's do Yeah, because I think what we want to do, all comparison operators are like binary operations. So we can make comparison a primitive operation, and it'll always have two, but it'll have this. Let's call it comp op, just to be clear. Okay, so this will be EQ. I don't need commas. EQ less than, nope, less than, equal, greater than equal. Not ideal. I would love to be able to use these symbols directly, but they are reserved in Gleam, and that's okay. So what we can say is comp is the operation is a comparison operation, and A is an expression, and B is an expression. What's not clear to me is whether, like Lisps, other Lisps, and an OR support an arbitrary number of arguments. And what would be the semantics of and with nothing? I would expect that would return false. Or with nothing would return true. But it's not clear to me. So I think that maybe what we'll do is we'll assume, so not, we'll just take one expression. I think that's pretty clear. And we'll take two expressions. Okay. And or we'll also take two expressions. Okay. So I think that we've covered all of the additions to the abstract syntax. So we added Boolean literals as expressions. We added if expressions that themselves contain expressions. And then we have the new primitive operations related to Booleans. So there's, maybe I'll just rename that to comp. Yeah, it's fine. This may get a little bit confusing, but for the most part, you only refer to the constructors, not to the types. It should be fine. I'm not worried. Okay. So, let's go back here. So, okay. Introduce string pass. The main event of this chapter is the explicate control pass that is responsible for translating ifs into conditional gotos, which is like always how you do it. Way back in university, I took a class which was microcontrollers, and you had to build the board and everything. And one thing that I learned pretty quickly in that class was oh my goodness, I am really mucking it up today. Was to use the different jump, like the comparison instruction, because we were using an x86 style processors and Intel 8051. I say x86, it's not x86, but they use the same kind of assembly language. You had J&E, J&Z, JZ, the different jump operators. And I think in this one, they aren't using those specialized jump instructions. They use just one jump instruction, and there's some comparison instructions in there. But yeah, for sure, the big thing is this explicate control will create new symbols to jump to in the program. So that's going to be interesting. Register allocation, interesting question of how to handle conditional go-tos during liveness analysis. So we will get to that. Okay, so I think that we've mostly covered this section, but let's skim through it real quick. Definition of the concrete abstract syntax are shown below. The elif language includes all of elvar. The Boolean literals true and false. Okay, so one thing that we didn't do. Oh no, we didn't. We don't have to because we're using Gleam's type at the abstract level. If we had a concrete syntax, we need to worry about #t and #f. Okay. So, right, it includes the if expression as well. We have the operators and or not, the EQ operation for comparing integers or Booleans for equality, and these for integer comparisons. So that this list here kind of tells me that there might need to be or it might be useful to have EQ separate from these other operations. However, given the overlap, yeah, I think it's really we're going to have some code in here that says is it EQ? If it is, then the types can be Booleans. Otherwise, it has to be an integer. I'm not sure if that's going to get ugly or not. Okay, so figure 4.3 shows the definition of interpreter, which inherits from the interpreter for LVAR. Now, we did not write, so we do have an interpreter for LVAR. It might make sense for us to spend some time today writing an interpreter for elif. Now, we don't have it for the other intermediate languages. We didn't do that. But that could be fun. And this was like partial evaluation that we commented out. Wow, 3 months ago. We've come a long way, folks. Okay, so let's copy this stuff out and modify. Now, what they did in previous chapters, as you recall, is they had this kind of like object-oriented thingy. Did I not copy that? Copy, please. Okay. So we need to fill this out. Okay, so if we're interpreting an expression, we need some more clauses here. So let's add the missing patterns. Now this cannot return an int, interestingly enough. Because we want to retain Booleans. So let's make interpreter value, which is going to be integer int or Boolean bool. We call it int value and bool value. Okay. And it's just saying they're not used. Okay. So we're probably gonna. Does it make sense to have programs that can be interpreted to Booleans? Probably. So let's make it public. And we're going to say iValue. Okay, so the other thing is that this env has to have an I value rather than an int. So, right, so this needs to return an I value. This operation needs to return an I value, and so forth. So we're going to have to do some unpacking here. That's going to be fun. Get var is going to return an I value. Okay, so they're probably doing some, or taking advantage of the fact that Racket doesn't actually care. That's interesting that immediately fixes that, but we have this is value, and then our if, this condition, then else. What we've got to do is this. And in Racket, recur just means call the function that you're currently in. Or rather, it's this. So we don't have to do that in Gleam. We can just call, and it tail calls if you like, if it's possible. Okay, so for if, we are going to have to do. Note that they have true and false here. We're going to have to call interpret expression on C, env. Then we need to handle what the potential return values are. So if it's a bool value of true, then we do interpret expression of the then clause. If it's a bool value of false, then we interpret expression of the else clause. Interestingly, they code THN and ELS for theirs. And then if it's an int value of anything, I think we should panic. What's the panic? Invalid Boolean expression. Now, if we are implementing their type checker correctly, then we'll never hit this clause. Like it should be an invalid program. So okay, so this function should work. We have covered all the possible branches of or variants of expression. Now we have to deal with operations. So this is going to be a little bit nasty, but let's go ahead and deal with this one. Actually, let's deal with the nastiness, and we'll start with the negate because it's the simplest one to deal with. So if we assume that this returns an I value, we're going to put this in brackets because we're going to have to do. We're going to do let assert int value and then we're going to say int value negative I. Why are we doing that? Because what we need to make sure that this expression returns an integer value. So we're going to have to do the same for each of these. Okay, so we'll say let assert int value is that, and we'll let assert int value the b value. Remember, this is an interpreter. We don't have, it doesn't have to be especially efficient. It can crash if things are wrong. But we are making, okay, so this is basically what we're going to do for the rest of these that have two, or that are on integers. Okay, and then we're going to say this is, and we have to rewrap it, a value plus b value. Okay, so this is, if we read an integer, we wrap that in an int value, and then that's correct. Okay, so now we're going to do something similar here, but these have to be booleans. So let's say this is bool value. Is that what I called it? Yep. And then we will say it's a bool value of AV and BV. I think it's, yeah. Okay, let's do or, because it's basically the same as and this is or. And not will be similar, but with only one argument. Oh, and we need A and B here. A and B. Okay. So not and then we will go not, or just bang B. Yeah, okay. So comp is a little bit interesting. In that this is operation and this is A and B. Okay, so I think what we want to do here is let's use EQ, and then for anything else they have to be integers, and then so what we can do is not match case. So if this is int value, then what we want to return is bool value, oops, of AV is BV, right? If this is bool value and bool value, okay, and then if they're anything else, then what we want to do is panic as I cannot compare ints with bools. Yeah, we'll say integer expressions are not equal to Boolean expressions. And hopefully we won't hit that, but then that one's covered. Okay. So now we know that this is only a one of these other operators, right? We know it can't be EQ. It has to be one of these. Therefore, and this is interesting. This is an interesting design decision, and that you could technically do comparison operators on Booleans, and you could, for example, Erlang and Elixir do this. You could have a total order of all value types. I say total order, a partial order. At the very least, you have an order over the types as well as the values within them. Such that you could say, well, a Boolean is less than an integer. We're not doing that in this language. So we'll do, we know that this needs to be an integer. And I'm sorry, I'm just going to copy. I'm tired of typing that. Okay, and then we're going to do case op, and we'll add the missing patterns, and we're going to panic unreachable branch because we should have gone to this one. Okay, and I'm going to put that down at the bottom. So here it's we're going to return a bool value of AV is greater than BV, and this one is also going to be bool AV greater than equal BV, AV less than BV, okay. Now, I suppose we could have done this differently. I just think it's important that when we're doing an operation that's not EQ, that we panic on Booleans, because we're not inducing an order on Booleans. They're either true or false, and there's no sorting of them, no ranking. Okay. All right, let's read their code real quick. Okay, so we took care of bool expression. We took care of if, right? If it's true, we interpret the first branch. If it's false, we interpret the second branch. And oh, that's interesting. They're saying if E1, okay, so they're not doing a direct AND like we are. They're going like if expression 1 is true, evaluates to true, then evaluate the second one. Otherwise, just return false. It's a short-circuiting thing. It's fine. We could do that. They also do a short-circuiting OR. Yeah, let's go ahead and do that. That'll just take a minute. So if we do case of A, E, and B, and this is the AND, if it's true, then we do So then it just depends on the right hand side. If it's a bool value of false, then we return that. And if it's anything else, we panic as integer expression not valid and. Okay, and then we can get rid of this. And then this will be really similar for the or, except reversed, basically. So let's do that. If it's a bool value of true, then we just return true. If it's a bool value false, then we have to evaluate the second argument and return that. Stop, please. My cat's very busy. Okay, and then if it's anything else, we say that that's not valid anymore. Okay, so then I guess for the other arguments, they're just saying, you know, interpret. I'm sorry, for the other expressions, they're saying interpret the primitive operation. Yeah. Okay. I don't know if that's any better, but we have an interpreter. All right, let's look at what they're saying. Okay. So right, this is what we're doing. So if E1 evaluates to true, then we evaluate E2. If not, we evaluate E3. Those behave according to propositional logic. Yeah, and that's what I didn't see before. They're saying they perform short circuit evaluation, which is fine. Like the challenge of that is that if one of your branches on those has a read operation and you expected to read in an integer, and it doesn't because your first part is evaluates to false or true or whatever, that could be a little bit confusing. Okay, but that's a worthwhile, you know, optimization for doing less work. Okay, with the increase in number of primitive operations, okay, we practice moving the code that differs for each operation in interp op. Okay, right, and handle and or separately. You know, it's fine. We do it all in interp op. We don't bother putting it here. Honestly, it doesn't matter. Yeah. I think it's that they were trying to keep that short-circuiting behavior out of this. But since we have exhaustiveness checks on this particular enum, then we have to produce all the variants even if we're evaluating it up above. So, yeah, it's fine. Okay. So maybe we should try out our interpreter. Yeah, let's go ahead and make a test. Yeah, we've got some tests in here. So new file, elif test. Okay. And then we'll say, let's see if they have any example programs up here. Maybe we'll just pull some example programs and test our interpreter. Elif interpreter test. Okay, and we're going to import UC langs elif. All right, let's construct this program. And I think that we need program, we need we don't need this type yet. We need comp, we need primop, actually let's just let's start with this, and we're gonna have a program here, and it's going to take an expression. So this is going to be which the prim is an expression, primop. We have plus, actually. And plus is going to take int 10. And then it's going to take, let's break this out. So we can see this more clearly. Okay. And what we're going to do is let's go ahead and, before we type this entire program as abstract syntax tree, let's copy that and put it in a comment so I don't have to keep looking over at it. And then also define our let's figure out what this should be. So 12 and 20 is 32 negated, so minus 32, and 10, add 10 to that, and you should be negative 22. Okay. Okay, so that's what we should get from this. Obviously, this is not correct yet. Okay, so plus takes 2 arguments, and here we're going to have an expression which is, let's go ahead and import prim plus int value, bool value. We want all these constructors. Interpret we're going to need negate. We got plus negate. Yep. Okay, that should be enough for now. And then let's unqualify. Okay, I haven't done that yet. Okay, so this is a primitive operation, which is negate, which contains a primitive operation of plus, which contains an int of 12 and an int of 20. And there, I think that's our entire thing. Plus 10 12, 20, negated. All right. So let's run this test real quick. Okay, so it's just saying that we have stuff that we didn't use. So let's unqualify that, and we can unqualify that. Okay, let's do another one real quick. Bool interpret bool test. And let's use another example of theirs. This is okay. We're going to make a program, and here we're going to need and, not, and bool, right? So this program is primitive and, right? And the first argument is a primitive of not, and then that's going to have a bool of false in it. And then the second argument, let me break this out so we can get the indentation correct. We can see that clearly. Okay, and then the second argument is bool of true. There's a problem here. And it's actually that I have a parenthesis in the wrong place. Okay, so this one should be simple to evaluate. If you have the negation of false, you get true, and true, true returns true. Bool value of true. Okay, so let's run this. Okay, so that passes. Interestingly, it doesn't run the test directly, so it runs all the tests. That's okay though. Okay, so we have a basic interpreter. We can't, I don't think we can really test panics. Because we would want this to not type check, right? Okay, let's just look at this real quick. Yeah. fx plus is the function in Racket to add two fixed nums. So fixed num being like the smallest kind of integer, I guess. Okay, and here they're testing for the type. Like, we have to be explicit about it because we're statically typed, even though we're interpreting the language, the AST. So yep. Okay. All right, let's start reading about type checking. In the meantime, I would like to do one more test here. Conditional interpret conditional test. and let's come up with a program. So let's say we'll say if, and this is I don't know, less than 5, 2. Then we want to return 42, else we return 3. So this is really simple one, but writing it out will be fun, just like the others. Okay, so we have a program. And what we're expecting the result of this program to be, because 5 is not less than 2, we expect the answer to be 3. So let's go ahead and interpret the program as our test condition, and we should get int value of 3. Oops, 3, not e. Okay, so here we're going to have if, and that takes 3 arguments. And let's put if in here, please. Okay, and we'll unqualify that. Okay, so this takes an expression. So this is going to be, so that returns a prim op. So we need prim, which is an expression, comp less than. So, and then that takes 2 expressions. I'm sorry, less than is the first one. Int of 5, int of 2. 42, int 3. Okay, so something's wrong there. So we need to import comp, and then let's import LT, and then we can unqualify that. Okay, so doing comparison less than should equal int value. So let's run those tests again. Okay, so now we have that test. This shows that our if logic is correct. Okay, so let's start reading about, let's make a commit real quick. Test, and this is chapter 4, and we'll say 4.1. L if language and interpreter. Okay. We're cruising along. All right. So thinking about type checking, it's helpful to think about type checking in 2 complementary ways. A type checker predicts the type of value that will be produced by each expression in the program. For elif, we have just 2 types, integer and boolean. Remember, we put that in here as an enum. So type checker would predict that this produces a type of value type integer, whereas this produces a type boolean. Now we just use those examples in our test for the interpreter, so it's all good. Okay. The sub expression. Okay, so a second way to think about type checking is to force a set of rules about which operators can be applied to which kinds of values. For example, our type checker for elif signals an error for the following expression. The sub expression that includes plus 10 negated plus 12 over 20 has type integer. The type checker enforces the rule that the argument of not must be an expression of type boolean. We implement type checking using classes and methods because they provide an open recursion needed to reuse code as we extend the type checker and stuff. Okay, so we're not going to be able to do that. We have closed types. And they're saying this is analogous to the use of classes and methods for the interpreters. The thing is, it's actually, even keeping it completely functional with closed types, it's not that much more code. So I don't know what the motivation for that is, other than that's a nice feature of Racket. So we're going to skip that. So separate the type checker for the LVAR subset into its own class, shown in 4.5. So we need to scroll down to 4.5. The thing is, LVAR doesn't, like, all the types are integers. So what we're going to need to do is we're going to need to have a place to put the type definitions. I'm not sure what that business is about. Okay, so they're just saying here that the type of the body, so this is saying if we're matching this program with this constructor, then, okay, so then it's saying type check the expression body with, starting with an empty environment. You want to check that all types are integers. Now, it's like literally, if you look at lint, it's literally not possible to create an expression that isn't an integer type. So it's kind of a no-op from this respect. And then they're saying check type equal is integer of body. So they're just saying this is the type checker for the program. It checks the expression that is the body of the program. So we look at the expression here, and it's saying, okay, and we've got an environment. If we have an integer, I don't know what this values function is. Where's this values? This must be some racket thing that I don't understand. Okay, so this is about what I expected, just glancing at this. Also note, there looks like there's some macro business going on here. I don't want to be involved in that. That may be partly what this define values is also involved in. It's not clear to me. But the essence of it is you go into the top level expression of the program. You have excuse me. You look at that expression. If it's an integer, then the type of that is integer. If it's a variable, then you look up the variable, its type, right? This env is the collection of types for each variable. If you have a let expression, then you evaluate the type of the expression, and you set that type to in that environment to X, and then you type check the body with that in the environment. So if when it goes and looks up what is the type of X, you get that from the let, right? And then for primitive operations, it's like look at, let's see, look at all the expressions here, type check them with the given environment, and then type check the operator, right? Okay. So that's for lvar. We're not really type checking lvar. And I honestly don't know that because lvar only has integers, that it's that useful. So what we should do is create a type checker for elif. So here they're going and they're extending the, the lvar one. Yeah, so then it's like they can call super on it. Okay, so I think what we need is to define these functions. So let's check type equal. I honestly think we can just do integer or boolean, and are they equal? We'll see. Okay, so let's start creating type checker, and we'll call it type check program, and that's going to take program. And this should return All right, let's read a little bit more because I want to understand what this define values thing is. Let's see if we can get there. Okay, so separate the type checker into lvar subset for its own class. Type checker for elif is shown in figure 4.6 and inherits. And because they have those open types or a lack of types or simpler types in Racket, they don't have this problem that we're going to have to tackle. Okay, each type checker is a structurally recursive function of the AST. Of course, that's what you would do. Given an input expression E, the type checker either signals an error or returns an expression and its type. Okay, so it returns an expression because there are situations in which we want to change or update the expression. Okay, so if you wanted to do partial evaluation or something like that. So what we're expecting is, and I think that we can probably use a result here of a program or nil. Did not do that right. I am doing this wrong. Okay, result dot result. Is that not right? It's not angle brackets. We're not in Rust. Okay. Error. Okay. So honestly, I can probably just put to do here. We can potentially make this be an error type at some point. And maybe we'll just do that. Let's say pub type error, and we'll just make an empty one for right now, and let's just say type error. And we might want to return we might return something else. And that way we can go into you know, the interpreting expressions, or not interpreting expressions, type checking expressions, and, you know, potentially return type errors for individual operators and so forth if they don't match. Okay, so it returns an expression because they're situated right. So next we discuss the type check expression function. The type of an integer constant is integer. To handle variables, the type checker uses the environment env to map variables to types. This is similar to what the interpreter does, just like memory locations for the types instead of the values from evaluating expressions. So consider the case for let. We type check the initializing expression to obtain its type, and then associate type t with the variable x in the environment used to type check the body of the let. Thus, when the type checker encounters a use of variable x, it can find its type in the environment. Regarding primitive operators, we recursively analyze the arguments and then invoke type check op to check whether the argument types are allowed. Okay. So that's the basic strategy. So we're going to have type check expression, which is going to take an expression and an env, which we're going to say type env is a dictionary, and that's going to be because this is just variables, it's going to be a dictionary from string to type. And we'll say this is type env, and this is going to return a result of an expression or a type error. Except this is not going to return a result of an expression. It's going to return a result of an expression and a type, or a type error. And we'll put to do there, and then type check op. That's going to take a prim op, right? And it's going to return a result of a pair of a prim op and a type or a type error. Okay. So, several auxiliary methods are used in the type checker. The method operator types define a dictionary that maps the operator names to their parameter and return types. The type equal method determines whether two types are equal. I think yeah, you can do direct comparison between variants, empty variants, so that we don't need that. Type check op method looks up the operator. Okay, I don't need that dictionary. Like, we can do this direct in code. I think that, you know, there's going to be limitations for when we expand the capabilities of the language, for sure. We are going to pay that cost. The trade-off we're getting is that at this point, these types are strict and we can't go outside them. And that's actually going to reduce some of our work. Okay. So, let's go and let's move this up just for my sanity's sake. Okay, So if we are the interesting thing here is that I think we need to does this it doesn't override type check program. Okay, so this is interesting. I think what they're saying is that the root expression in an elif language also has to be of type integer. You can't return Boolean. Okay. And then that goes on to do cif. So we're probably not going to get to that today. We have about half an hour left. Let's see if we can do a very simple type checker for program. So and down through recursively through these other operations. Is it primop? Yep. Okay. Okay, so for type checking a program, we need to take the root expression, the body basically. So what we're going to do is we're going to do case type check expression p.body, because that's the expression, and we'll make a new dictionary. And then if we get expression, if we get OK, expression, and we don't care about the type, then we're going to return a program containing that expression, and we're going to return OK. Otherwise, if we got an error, then we'll just return that error. Oh, right. So this is I was trying to do something that doesn't work. So if we get the error, we need to rewrap it because it's not the same type. And we don't have question mark like we would in Rust. So we can't just automatically convert them by rewrapping. So we have to rewrap ourselves. I think what's interesting here is I think maybe for the sake of staying close to what the original plan was with these languages, just integers, maybe if we say it's an integer, then we can return OK. Otherwise, we need to return an error, type error. And we're not going to really be able to say why that is here. It's just this check type equal. It's checking whether the body is of type integer. and then it's producing an error of some kind. Like we're not going to have that that sort of exception raising thing here, and we don't want to. We want to return type errors. Now, but this is also telling us what the contents of this type error should be. It's that we got something that we didn't expect, right? So we can say expected is a type, actual is a type. And then what we'll do here is we'll say, if we don't know what we don't care what the expression is, this is Boolean, right? That's the only other possibility. And we'll say the expected was integer, and what we got was Boolean. I guess that's okay for now. Okay. So then, but that will also let us at some point, like, you know, pretty print this and so forth. Okay, and they're saying it's putting the expression in there. The offending expression. Okay, so maybe what we'll do is I don't really like this, but we'll say expression is an expr, and then here we'll say p.body. The other possibility is that we do this. Yeah. Okay, so that's the type check program. Right now we're only supporting integers. Okay, so if we now we need to go and type check expression, and again this is not going to be a direct one-to-one, but we're going to do match over that and add all the patterns. So if it's a bool, then what we're going to return is OK of E and Boolean, right? If it's let's put the simple options up here. If it's an integer, we have OK. And we're not going to modify the expression, and it's an integer. That's easy enough. And then there's the var possibility there, right? Okay. We're going to return E, and then we will do there was something that we did, get var. Okay, I'm going to say v. Okay, this is going to be let assert OK t from dict get. Dict get takes a dictionary and the key. Yeah. Okay, so we're going to take E and V, and then V, right? And then we'll say this is OK, the full expression, and then the type. Okay, so this is, you know, we're just making sure that it has been assigned in here. The other thing that we could do here is potentially we could make a new, we could say unbound variable, and then the name is a string and the expression is an expr. That maybe is not that helpful. Maybe let's just say unbound variable as a type error. I mean, it's totally a type error. So then here we could say, rather than let assert okay, we can say case of get that. We don't have to panic. We can say if it's okay of t, then we return that. Otherwise, if it's error of anything, which should be nil, I think, then we want to return error of unbound variable b. Okay. I think that's probably the right way to go there. So now, let's look at let and primitive operations. So for this, we're going to just delegate to type check op. Right? Except that that returns primitive operations. So what we need to do is case of okay op t. Then we need to rewrap it in prim op t. Then we need to return. We need to rewrap that. Okay. So so for type checking a primitive operation and that succeeds, then we rewrap it. So now for the let, which is going to be interesting. Okay. So if x is the variable, e is the expression, body. Okay. So if we say case type check expression of e with the e and v, if that returns okay, then we'll do the rest of this. If it returns error, we'll return an error. Okay, so if it succeeds, then what we do is type check the expression of the body, right? Right. Setting, so we say dict insert. Here, we're going to do type check. We're going to have to do another case here. Of body. And we'll say dict insert into E and V X T. Some nested cases here I'm not exceptionally happy with. We could potentially do result.try with the it's sort of like the do syntax. Yeah, let's give that a try. I forget how, oops. It may not work because it may need to do this rewrapping stuff. But is it with? No. What is that Gleam syntax that's so cool? Oh, by the way, Gleam 1.11 RC1 is out the other day. So have a look at the stuff that's coming. It's looking pretty dang cool. Let's look at the docs. The language tour context. It's use. Okay, so this use sugar. Right, so this is kind of what we're trying to do. The problem with being that these don't necessarily return the same result types, we might not be able to use this syntax, but let's give it a shot. So I'm going to comment this out before we go forth. Okay, so we're going to say use, and this is E1T comes from result.try of type check expression E and B. Okay. Right. Okay. So then we're going to try, if that's okay, then we're going to try body1 T result.try type check expression of body and dictionary insert env xt, and then we'll say and we just return body1, or not body1, we return let xe1 body1, right, and t. Now what's the problem here? Did I mean to wrap this in okay? Yes, I sure did, but isn't that what your result? Oh, it's result map. We want result map, not try there. Okay, so that's just a little sugar for this sort of like nested case things with results. That's pretty neat. That'll save us a lot of mess here, right? Okay, so now we've done it for let, and we have the primitive operations there that we can take care of. So let's do it for if. So if this is the condition, then else. Okay. We might be able to have this use syntax for if. I'm not sure yet. Let's see what they do in here. So for the type checker for if, so the condition has to be Boolean and then and else have to be equal. Yes, thank you, use. I didn't realize you were watching. Hello, Miha. Okay. Yeah, so let's go ahead and do this. So we're going to we'll say C1. I'm just using 1 because we don't have the tick or the caret as part of symbols, variable names. Okay, so I do have a problem here. The result of this is the type of body, right? The result of the let expression. I needed to fix that. Okay. So the type of the condition, result.try, type check expression condition E and B. Okay. And then I don't think that we can do Boolean here because let's write this out as cases first, and then we'll convert it to use later. I think that's the probably the easiest way. Okay, so we can do case type check expression of the conditional, and this one may not. Yeah, this may not allow us to do use, and that's okay. We don't have to do that everywhere. Okay, so if this is C1 and it's Boolean, then we continue. If it's, we don't care, well, C1 and integer, right? Then we're going to return error, type error. We expected a Boolean, we got an integer, and the expression was C1, right? Okay. If it's an error, then we return the error. Okay, so for this, we're going to say here's where we can put the use. My cat is very busy. Okay, so we'll say type TT for type. Yep, thanks for typing out for me. Result.try. Okay. We're going to type check expression of then. And the else branch, the type of else, result.try, type check expression, and so forth, else, E and B. And here's where we'll do map. I don't know if bool, let's go back here, docs, where's the standard library? Docs PM. There we go. Okay, so there's this guard. Yeah, you can use guard. Is that what we want? Yeah, probably try instead of map because you need to error if the branches have different types. Yeah, the question is, do we do I think we want bool guard. No, 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 no. We don't want bool guard. I might be trying to be too clever here. uh, yeah, it is. It is still try. Okay, so if those are equal, then what we want to return is we want to return let of c1, t1, e1, and this is we're going to say okay, and then except this needs to be an int tuple, and the type is really the type of the else branch or the then branch. Honestly, they're the same. So if it's false, then we're going to return error, type error, and again, this goes to this like they're short-circuiting, blowing the stack, unwinding, so forth. Check type equal. So we are expecting that the type of the then is the type of the equal in the expression. What's wrong here? Oh, this is not let. This is if. Okay. Not the best, but I'm okay with it. I'm okay with it. Okay. So, so let's do type check op, which here, they did this whole dictionary thing. Yeah, use is totally like a drug. It's like with and elixir, and then you realize, well, it has this very narrow use case. Use is probably a bit better because it's a bit more like do syntax in Haskell, where it's pulling the function that you would pass to bind out into the next expression. So yeah. Anyway. Okay, so we're going to do type check op. And oops, not match case. This is a problem of using way too many languages. Okay, so here we're going to need to put in a case here. Okay. So this is really, I want to put this one is fine. There's not really anything to do here. So this is just going to be okay of read int. Yeah, nothing special there. Okay, for not, the expression should be let's do use. Except we don't. We need to make sure that it's a Boolean, right? Expression of E, E and V, and then if it's okay, E1, Boolean, then we return okay of not E1, Boolean, right? If it's okay of E1 integer, then we're going to return a type error. error. This is where, like, maybe we could do that result try thing with use. I don't know. Error, type error, and that is going to be we expected a Boolean, we got integer, and the expression is EV1. And if we have error E, we return error E. What's wrong there? Just that we don't. What did I do wrong? Result of fun int to expression. Oh, integer. Okay. We're going to need probably a better, you know, the other possibilities that we could make this check type equal function and then put it in result tries. That could be a possibility. Let's go ahead and make that function, and then maybe this can clean up. Okay, so this is type A is a type B is a type, and E is an expression. And this is going to return a result of bool. Actually, it's going to return a result of nil, right? Because we just want to guard or type error. If it's true, return okay, nil. If it's false, then we return type error, error of type error, A, B expression. Okay, so what we should do here is let's unfurl this with use. Okay, so we'll say use E1 type of expression is result.try type check expression E and B. And then we'll say use check result try. Actually, no, it's result map check type equal of what we expect is Boolean, and we got type E and E1 is the expression. And then we'll just say that's the expression. Okay, did I do that wrong? We'll just ignore the argument. The other, yeah, we can't really use guard, bool guard, I don't think. We're going to call that function if the given bool is false. Otherwise, return a default value. And what we want is like the inverse of the guard. Can you use this in the other place as well? Yeah, I think what I'm going to do is go up and make this check type equal function in these other places, like here, for example. So let's go ahead and fix that real quick. and we'll say result map check type equal, and this is TT, TE, and the expression is our original expression. And then we'll say if all those things are fine, then we get this. That's pretty nice. I'm liking that. We could also, since we've got this same pattern here, we could say use C1 type of C result.try type check expression cond env, and then we can say use, we don't care about that variable, result.try check type equal of we expected boolean, and we got TC, and the expression is C1. And then we can get rid of these clauses, and that's pretty flat. That looks nice. And that's actually closer to the code that's in the book, in a way. Like, type check the conditional expression. Is it a Boolean? Type check the then, type check the else, make sure they're equal, and then finally return that. That's super nice. Are we doing that anywhere else? We can turn this into result. Result.map type check op. I need the brackets there. Okay, and then here it's just prim op t. That's pretty nice. Except I need that brace there. Yeah, that can stay a case. Yeah, that's cleaning some stuff up. I'm glad I went ahead and did that. So now we can go A1 type of A is roll try type check expression of A env, and we can do the same for B. And then we'll do this has to be Boolean TA1. And here we can do map, right? Because we're just going to return, if it succeeds, we're going to return and of A1, B1, and Boolean. Did I do that right? Oh, well, it helps if I do check type equal in here. Okay. I don't know if this is good code. I'm having fun writing it. I think we can go to the top of the hour, and hopefully we can finish these out. Because I think that they're going to be straightforward. Like, this is actually going to be the same as not. So let's move that up. Right? Okay. And this will be negate. Right? Okay, so or is going to be the same as and. Just changing the wrapper. That saves us some time. Minus and plus are going to be the same, right? They both have to be integers. But let's do, oh, shoot. Okay, so let's do this one. And we'll copy this for now, except we're going to remove this type check. We're going to say TA and TB have to be the same type. In expression E. And then we will return comp EQ of A1, B1, and the type is always Boolean, right? Okay, so now we can kind of copy this, except, I'm sorry, it's more like this. And this has to be, these have to be integers. And this is A and B. Okay, that's not that hard. And I think that we're going to, we actually, interestingly, we don't care about the operator there. We only care about equal because those, this is, this, remember, this has to be an expression. Oh, I called it P, not op. Okay. Nice to have the type checker there, making sure I didn't make garbage in my error. Okay. So minus and plus is going to be very similar to this. So let's just do that. So this is A, B, they both have to be integers, and this is going to be minus of A1, B1, and the type is going to be integer. And now we've done the work for plus. We just have to fill it out and make the changes. There might be better ways to do this particular step, but this is actually not bad. Especially since we decided to make that check type equal function, which returns result of, you know, potentially type error. Then we can throw uses and result tries in here, which is great. Okay. All right, let's look at this and see if we missed anything. Right, and the only reason they have this whole like class override thing is so that they can just put in the clauses that they care about to extend the language and then call to the parent one. But since we've got closed types in different modules here, we need to treat them separately. We may, as the language expands, end up copying stuff, refactoring, so forth. I fully expect that to happen. Okay, so we're gonna have to create a lot of potential test cases. Yeah, so our exercise, where did they say it, is up here. 10 test programs. So let's go ahead and make some tests, and then we'll call it a day. So we're in the if test. If so type check program test. We should have, let's make some, what's wrong there? Unimplemented function. Okay. So let's make some programs that should fail. So we want to, this should not type check, right? and true, false, true should not type check. So this should be a type error. It should be expected integer got boolean, and the expression is, actually there's no parens around that. The expression is bool true, right? I just want to write these out so that we can write the test for them. So, right, so what I'm thinking about here is like things that are, the expressions are internally consistent, but where the value of the program is a Boolean, because we've insisted that the program has to be of type integer. So here again, these are going to be the same, except it's not going to be bool true. It's going to be prim op, or prim of and bool false, bool true, right? What else can we do? Let's say, like, if t false, false. Not especially interesting, but what we expect there is basically this. I think it'll be the whole expression. So it'll be if bool true, bool false, bool false. Let's make a one that's a little bit less obvious. Let's do a let of, I don't know, x is 42, and then what we're going to return is less than 42, 5. So that's going to be return a Boolean, and this is going to be another, we expected an integer, we got a Boolean, and this is going to be let of x int 42 comp is a prim op comp less than int 42 int 5. Okay, those are some good examples. So we can actually use where it happened as the program, right? The fallible expression. Okay, so let's say program of bool true, and we're going to say type check program should equal this, error that, and we're going to have to, I want to enter type error and integer Boolean. Okay. Let's just run this and see if that passes. Okay, I'm not importing that, so we can remove that. So that did do what we expected. It seems that that is, it's going to treat the whole body as the expression in the type error, which is fine. Okay, so and let's let's unqualify that. I don't want to convert to function call. Let's do type check program. Did I make those all public, those type checker things? I did make them public. That's probably fine, so we can test them. Okay. And this is the error that we want. I wonder if there's a should error. I guess B error. And that'll return the error. I don't know. How do we feel about that? Let's just do the should equal for now. Okay, 2 more cases to implement. Okay, so program, here's our error. We're going to type check program should dot equal, and this is our error. Okay, so this is our program. What's wrong? Yes, I did. Good suggestion. Okay, and our last one. Okay, and let's use this. Yep, that's our program. Okay, what's wrong here? I'm missing a parenthesis somewhere. I need one there. Anyone there? Okay. Right, so I need to import let. Okay. All right, let's run our tests. Okay, interesting. Okay, so I did equal. That is a bug in our type checker. And the reason it's a bug is that. So we needed to propagate that op. That would have been a bad thing to come up with. So nice to find that bug. All right, this is a good place to stop. Thank you for hanging on to the end. And we're going to say this is chapter 4.2. I want to write more tests, so we want to write we want to test internal expression type errors, right? So we'll still use the, I did expose this stuff, but we'll want to test things with, like, in a let expression, assign a variable to one type and then trying to use it with an operation that it's not compatible with. We'll want to check, using booleans in operations that are only valid for integers, and as well as the opposite. So that would cover the operators, the primitive operations. And I think that we'll probably want to have a bunch of happy path cases. just to cover all of the stuff that we've done in there. So we can do that next time. Type check if language. All right, and oops. Okay, so that is up to date, and I will quick organizational bit. I will not be around next weekend. I'm going on vacation. But the following weekend, we'll continue where we left off. We'll finish these tests, and then we'll start looking at the other passes that we need to do in here. So thank you for sticking with me, and we'll see you in 2 weeks.